Alright, time for another DraftPhysics.com video presentation. So this will be about springs and all these experiments. So we have these different experiments done with springs as a source of energy and as a collector of energy. So scale, collects energy. But what it does also is that it oscillates. And so if I do put mass on a scale, let's say I put a 1 mass on and then I put a second mass on, they're same masses, and I have now a reading on the scale that says 2 or whatever, and then if I could instantaneously remove one of those, it sort of points out the importance of quick releases when you think about it, is that you really do have to get rid of it instantaneously to get the effect. Then the one mass is sitting there under 2 pounds of pressure. And what's the expectation? Well, the expectation would be is that it's going to overshoot. So it's going to, it's going to go back to 1. But it's not going to go back to 1 by just slowly rising and going to 1. It's going to go to 1 by overshooting 1 and then going back and then oscillating. And you're saying, well, how can it go past lighter than its actual physical weight? Does that mean it sort of has to have more energy? And the point would be is no, because the energy, okay, is based on the notion of free falling. That's sort of how weight is calculated, is the gravitational pressure, and it's kind of, you acquire it by falling. You can measure how much energy there is, and so what's really happening is when it goes back up, it's not going up at the same speed. That's why it goes more distance. It's because the velocity is less. So it rises slow. So when I remove the one mass, it won't rise at the same speed, the momentum of the energy. It will have, it's miscalculating. Let's just put it that way. So it's not a converter like a lever. It can't convert the accelerations. It just gives it, so it gives it a slower acceleration but more distance because it's more durable. There's more torque, you could argue. So it pushes past, but it's pushing past at a slower speed and then going back down because gravity says you went too far, and then it goes back up and then back down and then settles on the speed. So something I didn't realize until 20 minutes ago. Anyway, just trying to figure this out. So the Gosling character has done another video trying to defend his measurement device without actually showing how the measurement device works, showing that it works. He's trying to indirectly prove it, and in doing that he did do some weird things in the sense that he changed the number. So what he did in an experiment before came up with a number, say 5, and the same thing now has 5.5. So the numbers have changed, which makes you wonder if your experiment has that much error in it, there's probably a problem somewhere. So there's lots missing from the experiments, and so I just did a rough trying to figure out their view of how the thing works. So if somebody can, momentum makes it simple, right? You have a certain amount of pressure, instantaneous pressure on the scale created by momentum, and you could say that one mass going one velocity is 10, a 2 mass going one velocity is 20, a 1 mass going 2 velocity is still 20 because it's the same momentum, and then 2 mass going 2 velocity is 40. And their calculation is somehow that you only do this 1.4 thing. Okay, so the 2 mass, if I double the mass, I only get 14 on the scale. The scale only reads 14 instead of reading twice, because it's, as momentum would. And then again, if I double the velocity, I do get the same number. Okay, so somehow doubling the velocity will read on the scale as double, but doubling the mass won't, and their argument is because it's 4 times the energy or something. Anyway, and so these are the numbers I got for them. So if it was started, if we said a 1 mass going 1 velocity read 10 kilograms on the scale, you know, what would the numbers be? And I just want to know if they're going to confirm that these would be the number 14, 20, 28 or something like that anyway. And that would equal, you know, 2 kinetic energies is 14, 4 kinetic energies is 20, 8 is 28, that these kind of numbers fit with their view of things. And then here I'm just doing the simple experiment where I just say, okay, I put 10 pounds on a scale, and then I add 20. So now I have a total of 30. The scale goes down to 30. And if I could instantly remove the first 10, what would the 20 do? And clearly the 20 is going to go lighter than 10 and then come back. So it's going to do, you know, it somehow is going to go provide the illusion of the object being less light, less than 20 pounds. It's going to weigh less than 20 pounds. And you know, the argument is that's because the oscillation is a slower speed. It's not the same momentum that the 10 would shoot off at. It's a different momentum, different speed, a different velocity. And that's what messes it up, makes it more complicated. Alright, so the other point I wanted to make about this whole dropping things in gravity thing that I have made before, but I think needs to be reiterated because, you know, certain people don't wish to take any of the facts at all seriously, and they're real facts. So the trick is when I do put something on a scale, the fact is it weighs its weight. So I have to deal with the fact that it weighs something, okay, and that's part of anything I'm going to add. So if I'm going to add a velocity to it, I have to realize that in the spring is still its weight. So in the experiment, when you're going to drop an object, okay, a distance, you have to account for the fact that when it hits, it's not only this, okay, it's acceleration, you could call it if you wish, but you also have to account for the fact that it weighs something even without the acceleration. So when it hits the scale, okay, it's going to read not only the acceleration, the energy from accelerating, but it's also going to just weigh the weight. The weight is also going to be included. So if this is 10 pounds, the object, you have to recognize that whatever compression you get on the scale, you have to subtract 10 pounds. Because there's 10 pounds of movement that doesn't have anything to do with this acceleration. So if you want to know what this acceleration is, you have to subtract the actual weight of the object. So when you do these conversions, that's the tricky part, is that I convert from, I'm going to use the compression from one object to replace it with some other object. Okay, so the trick would be is if I drop a heavy mass in, all right, and now I'm going to do a half mass to launch out, that the difference is the heavy mass is built into this compression. The compression I got had included in it the weight of the heavy mass, and now I've reduced the heavy mass, so now I have the expectation that the compression is now reduced not only by whatever energy I put in, but the mass itself. And so this is essentially, I have stored in the spring a little bit of extra because I have the extra from the heavy mass. So doing the experiment in gravity creates this artifact, whatever you want to call it, this defect, where the half mass is going to get the advantage of you have essentially removed the weight of the 2 mass and you've replaced it with a half mass, so you've gotten 1/2 the mass is gone essentially, and so that little extra bit of energy, so you can have the expectation that this would leave with a little bit more energy. And if I did the reverse, if I have the light mass going in and I replace it with a heavy mass, I can expect that I'm going to lose a little because now it has to account for the extra weight of the heavy mass, and it's going to waste some of the spring's compression because of that extra heavy mass. So I'm not going to get the same back, I'm going to get a little less back. So it's a little minus one way and a little plus the other way. So it always has to be figured into this calculation when you're dropping the masses. You have to figure into them a subtraction of the actual weight of the object. That's another point to make in the experiment. I mean, you know, the Ian Gosling experiment, he has this scale right there, you know, that he's measuring with. Why doesn't he leave the weight on the scale and just make sure his scale's reading a right number? You know, a 1 pound weight versus a 1/2 pound weight, and see if you can see that on your scale to start with. And that's sort of giving you the indication that this weight is always going to be there. It's not going to disappear from the experiment. So the static weight of the object will be in the reading you get. When you let the weight go and fall, it's going to include the weight of the object. So obviously if you're dropping a heavier thing, you have to acknowledge that you've added a little extra to the reading on the scale versus the light thing. Alright, so that problem goes away if you use some sort of pendulum system or some other, you know, some sort of vertical system to bang into the scale. Then you don't have to worry about these weight issues. But you still have the problem that the spring isn't as good a converter, let's say, as a lever, and it tends to want to oscillate, and that the energy going out won't be complete. Now you could see that in the Dispar lab videos. When the lighter car went in and then left, you could see the spring doing quite a bit of wobbling, and that was mostly because the spring bent, you know, when it went in, and so when it came back out it was wobbling, which just indicates that is an energy that's going into the cart. So it's just sort of a little giveaway that this is a little more complicated than you know, we'd all like it to be. Alright, so I think I've explained the two problems. So one problem is just because of gravity. You have to do this figuring for the fact that inherently the spring compression created by a light mass, okay, will not lift a heavy mass exactly the same energy, because it has to account for the fact that you've placed a heavier mass on, and that heavy mass means the displacement. It's stealing part of your spring compression. So the spring compression won't be the same amount when it's pushing the heavy thing. And the inverse, where if you calculate with a heavy thing, you let the spring fall with a heavy thing, it's going to compress more, okay, than the actual, just the momentum that went in. It's got the weight of the object, so when you replace it with a lighter mass, you have a little bit of extra energy from the fact that the heavy mass was put in, and you've got a lighter mass, and it's going to want to leave with a little more energy. And then the other problem, which is just about how springs release energy, and whether they release it at a perfect relationship to the size of the mass. And I guess the argument would be is that there seems to be that springs do move objects a little slower than what would be the ideal exchange speed. So like a lever, the argument is it does a fair conversion. Let me just erase some of this. Because it matches a velocity to a distance on the lever. So the idea is that the lever at twice the distance, okay, can basically exchange the deceleration to acceleration rates. So if I put a half mass twice the distance, what I'll basically do is match the deceleration of this object, because it'll move exactly half as much as the other one will move, so it matches the velocities. Spring isn't quite doing that. It's not going to be able to match the velocities as perfectly, so when it's pushing something heavy, it's going to be or something light, it's going to be a little less than perfect in terms of matching the velocity to the mass and such. But anyhow, how much of a difference it makes, I don't know. So that's the real problem, is that springs have never really been tested. I was surprised to learn that tennis balls are only 75% efficient in terms of you throw them in with a certain energy and you only get 75% back. So we don't really have any tests of springs to see how good they are at even storing the energy. I mean, how much goes in versus how much comes out. Now, the Dispar Labs video has some indication of that, in the sense that he has numbers. So you could have a number like 456, and you would lose, say, you'd only get 400 back. All right, and so you could calculate that the 56 is 20%. So you lost 20%, so it's only 80% efficient. All right, I think that's a correct calculation. Well, whatever, something like that. So it's sort of indicating that they don't give back exactly what you put in. So there wouldn't be much expectation that you could, put energy into a spring, lock it, and then send something back with the same energy, because it's going to be at least maybe 15 or 20% less than what you're expecting. All right. So now I'll pause and see if there's anything to add. So I'm just saying that springs are, I think some things you can say don't make enough difference. Like even the mass thing doesn't make much of a difference in gravity. If you're going from, like say you're dropping a 6 ounce or a half pound, let's say 8 ounce, half pound object, and you're going to give it enough energy where it's going to read 10 pounds on the scale, well then subtracting the original half pound isn't going to make too much difference in terms of the number. It's only going to change it by a couple of percentage points. So in some respects all this stuff can be understood to be when it's important and when it's not important and all of that. Yeah, so I think a pause. I don't know if there's much to add. Alright, I think I'll add another example where obviously you can see where it's very subtle. So you have the classic air track experiment where you bang one thing into another thing with a spring, or not, but anyway, and it's elastic in the sense that you can get really tight numbers. Okay, I mean you can go in with 100 momentums and essentially get 99 out. Okay, I mean losing very little velocity in the transfer if the masses are the same, very little. So the argument is this breaks down as you start changing the masses, and the spring has to make more of a decision. Okay, this is pretty straightforward in the sense the spring's compressing at one end and it's going to release at the other end, and so you can sort of argue that there isn't much energy moving back and forth through the spring. It's not doing much calculating, it's just this easy transfer, and that the more complicated challenge for a spring is when it has to, in these other experiments that are demonstrating that it's not quite as reliable, that you're not going to get these perfect amount of conservation of the momentum. So like bouncing carts into carts that are uneven masses, and say even in situations where you have two things come in from different directions, whether you're likely to get the same kind of efficiency in terms of what you get out of the spring. And classically against the brick wall, the argument would be is that's the more complex one because it's a pure reflection. So where this is just a clear continuity, this is much more complicated in the sense that the energy is going into the wall and then it's coming back out of the wall back into the spring. You have to say, to some argument, there has to be some energy going into the wall and it's getting back reflected. So something comes in, it has to compress the spring, the pressure has to be rejected by the non-movable, and then it gets back into the spring and the spring relaxes. So it's a much more complicated event, and that's why the efficiency goes down. So you could argue that there might be a clear difference between this 99% you can expect here and the what may be 85% you can expect here, and that part of that is the fact that there's more going on in the spring here than is going on here, and the more you have going on, the more problems there are. So this is sort of relates to the idea of taking a weight and having a spring expand, and then it has to release that energy by stopping and then re-expanding. So it's similar to the brick wall. The device holding the spring is immovable, technically, and so it's essentially the brick wall example in terms of giving back. And you know, there might be, that might explain this huge difference in the numbers. Okay, so that's just trying to illustrate why this isn't as simple as, you know, personally I'd like springs to be more, you know, more reliable than this. You know, figuring out that there's these little subtleties is kind of irritating. So you know, maybe they're not the best conversion device, and it's better to stick with levers and hydraulics and other systems where there's not as much, it's not as complicated. Yeah. Okay, so I think that's probably enough, but I'll take a pause just in case I think of something else. Alright, just one more little bit maybe. So I was just thinking about the speed problem, like speed, how it affects a spring when you're going to compress a spring. And you can sort of understand that the faster you're going, the spring's going to compress different than if you're going slow. So if you're going slow enough, you could figure out that the coils are going to compress evenly. Like each coil is going to compress a little bit, okay? And then they'll all kind of proportionally compress. I should draw these bigger. Yeah. Alright. And so the compression will be spread evenly, and you can say, okay, and then there's a certain speed I get to with each spring. You know, that'll be different for each spring depending on its stiffness, where I'm basically just going to put the speed in, and the coils will smash against each other, and then the next coil will smash into the next coil, and the next coil will smash into the next coil. The rest of the coils won't really know what happened. These will just start smashing into each other. Alright, and that's a different effect, right? You're pushing the coils against each other. Now, how big a difference it makes, I don't know. And I guess it depends on the circumstance, but clearly there's a difference, that's all I'm arguing, between smashing the coils into each other and have the coils rub against each other and push each other than there is an equal compression in the coils themselves. So to some extent speed matters going in, and there's a certain maximum speed that you can expect the spring also has in terms of relaxing. So going from the compressed state, I should draw it more accurately, you know, the compressed state to the relaxed state. So the compressed state would be bigger and tighter. Okay. The compressed state to the relaxed state, you can understand that there's a certain maximum speed that the thing could possibly expand at. And again, it's going to tend to want to expand evenly in that case. So it doesn't expand unevenly. The coils will, if they're all smashed together, especially if you smash them all right next to each other, you could understand that each one will expand, okay, with the same little bit of pressure, the same pressure for each coil, and that they'll all expand evenly, you know, in terms of the amount they'll expand, and till they get fully expanded. You could sort of understand there would be this kind of pattern. But it just kind of depends on, again, then how they're rubbing against each other might distort that, because some of them might be crooked, some of them might be in the wrong direction, so they're going to be pushing in directions that aren't necessarily expanding the spring. And that problem would be is then that's not going to be creating momentum in the object. If the spring is pushing in this direction or pushing in this direction, it's obviously not going to be pushing as well in this direction. It's going to start losing a bunch of energy to directions that aren't the direction you're supposed to be getting out of it. So just another point to raise, that it's a little more complicated than just saying springs store energy and then release it. There's rules and there's a mechanical process that has its limitations, clearly. Alright, so maybe we'll just say that's it for the video. So I'm not going to, I think clearly the experiments are messy enough in terms of the details. In the case of the Dispar lab ones, clearly the spring is bending. So clearly the spring is kind of small. It's stiff and small. And instead of being able to equally contract, it's going crooked instead, which is going to give you a deceptive impression of its actual compression. And then in the case of the Ian Gosling, like I said, he does get different numbers. There is no, you can't see the actual reading on the scale. He hasn't demonstrated that the scale reader records accurately, and so the whole thing is kind of, I'm going to wait for something better, frankly, before I draw any conclusions. But I clearly argue that springs do, generally speaking, they're affected by momentum, and momentum does control their function, and there is no such thing as kinetic energy. I mean, the simplest argument is if I put a one mass on a scale, it reads 10 pounds. I put the second weight on, it reads 20 pounds. Clearly, I've only done 2 units of work. It's kind of insane for somebody to argue I have 4 units of energy, because I really can't have 4 units of energy in the spring. Alright, because I only did 2 units of work. It's free energy if you're going to make that argument. Alright, so till the next time and such. I could deal with a comment maybe just to dispose of it. These people, they deserve disposal, so I'll dispose of them. So this is some sort of Daniela. I think this is somebody who commented yesterday completely irrelevantly, and it's and rudely, and just stupid stuff like how big is your head actually? Some kind of nonsense. So just a waste of time. Oh, you shadow banned me too. I ban people who can't make a physics argument. So if you can't make a physics argument, I don't have any use for you. So if you want to argue my personality or some other bullshit, go fuck off. I have no interest. I have no obligation to correct liars. So if you can't say things that are accurate in your comment, or at least trying to be accurate, fuck you. I don't have any reason to waste my time arguing with assholes. And you're just clearly pointing out you're an asshole. I mean, to call somebody else an 8-year-old when you can't make a real argument on the actual subject of the actual video. Okay, I hope you reach the maturity people get at age 10 before you die. So, look at the videos being produced by the other side, okay, and then talk about maturity. It's just hilarious. Of old age, but I have sincere doubts about it now. And I could give a shit what you think. I'm sure your life is a mess, and you are, frankly, by any reasonable standards, a fucktard. I can't even share a link to another video. Just pathetic. So again, you can share titles. There's lots of ways to get around what YouTube does, okay? That's separate from me. So, fuck you. And I have an email address. If you have something important that I have to see, then send me an email, and I'll read the email. Alright? So if you really have to, if you're desperate to troll me an email. Alright, fucker? Alright. And get more upvotes. You do hilarious. So again, proving this is just a sock account, right? I mean, do we really think there's all that many people who read this piece of shit nothing comment? No chance at all. So, whatever. Fuck off. This is just such a waste of time. These stupid, pathetic trolls. Fuck you. Alright. Now what to do about this JG cap guy. So I say this is all crap-o-matics, right? So I just point out you're just talking shit. We just want to know, what the fuck do you think happens? All right, I dropped something from 4 times the height. Does it compress the spring twice as much? 1.4 as much? What's your prediction? What's your statement regarding the truth? All right. So he says, I didn't mention mass or springs at all in that comment above, which is only about kinematics. Well, who cares then? If it's not about what's compressing springs, then it's not on the fucking subject, asshole. Studied by Newton, Galileo, et al. Yeah, so you can keep saying shit like that, but Newton believed in momentum, okay? So fuck you. He didn't have any, he opposed 1/2 mv squared. So he didn't think anything was squared regarding velocities. So fuck this bullshit of bringing up Newton or even Galileo. Because they didn't believe what you believe. Suvat equations, not dynamics, which is about energy. So I'm just saying, you're obviously defending this mushy, silly, squared crap. If you want to argue about springs, that's what the fucking video is about, shithead. Continue to argue with experiments like Gosling's Stephen Bro and physicist Michael. I don't know what experiment he did. But anyway, don't direct your rage. It's not rage, you fuckhead. But anyway, frankly, I'm done with you. All right, you have something to say, you can email or you can post it on Brozo's channel. But these comments are not on the subjects. I've posted 7 videos now that are 4 minutes long. You didn't post a single comment on any of those videos. Well, I'll just delete this shit for now. But fuck you. Try to make a real argument or just fuck off. Alright? Obviously you can't make videos, you can't do anything constructive, you can't draw a picture of a lever and explain how it doesn't conserve momentum. Those are the things I'm interested in. I'm not interested in this fucking silly shit talk that you do with your fucking equations. It's useless mush until you prove some of it. And you're not going to prove it, okay, with your stupid words. You're going to have to prove it by linking to an actual video showing that what you say is the truth. Alright. So, enough of that. Yeah, so I don't think there's anything anywhere else that's of any interest. So, we'll leave it at that. And until the next time and such and so forth and whatnot. So we'll see. If the lever experiment gets done, that'll be a good one, right? Because, yes, if levers don't conserve momentum, then we're really on to something. Like, yeah, the universe really is fucked. Alright. So, till then and such.